Okay, hello class. In this lesson we're going to be looking at the inverse trig functions now. I've been saying that inverse functions are really a fundamental concept of Algebra 2 and um, and so I want to start off this discussion just really by talking about inverse functions again, just reminding ourselves. So if I have a function f of x, this notation denotes the inverse function where, if I have a function which turns yellow into green, the inverse function takes that same green and turns it into yellow, where the inverse function undoes itself. Here, let me fix this just a second here. The inverse undoes the original function. So if I have x squared, and let's just define x squared for x values greater than 0, the inverse function is the square root of x. They undo each other. I plug 2 into here, I get 4. I plug 4 into here, I get back 2. Okay. Now, the inverse of 10 to the x, that's, if you remember, log base 10 of x. Now, they have nice properties in the inverses. From a graphical perspective, the inverse is a reflection of the function over the y is equal to x line. So if I have this exponential function here, and if I reflected it over the y is equal to x line, I get the inverse. And in this case, the inverse function is the natural log of x. F of x will always pass the horizontal line test if the inverse function is to be a function as well. So the horizontal line test can be used on f of x. Now in this case, the inverse of f of x is going to be the same as f of the inverse of x, and so we have both of these equal to x. Let's give an example. 10 to the log base 10 of x is equal to the log base 10 of 10 to the x, which is equal to, in both cases here, x itself. Inverses help us solve equations. If you remember, log base 10 of x equals 5, I could then raise both sides to the power of 10, and so I get x is equal to 10 to the 5th power. So that's the idea. We use the inverse as a way of solving. So if I had, for example, sine x, or let's do something more interesting, x plus 3 is equal to 1/2, then then I could take the inverse sine of the sine of x plus 3 is equal to the inverse sine of 1/2. And so since these undo each other, I get an answer of x plus 3 is equal to the inverse sine of 1/2. Okay, so now let's actually talk about the inverse functions. We've seen these actually. We brought these up in class before. We have our inverse sine, cosine, and tangent written like this, but we can also, it's an equivalent expression, arc sine, arc cosine, arc tangent. So we have this function, y is equal to arc sine of x when, if and only if, x is equal to sine y. Okay, so we do have a bit of a problem though. The function f of x equals sine x looks like this, and it fails the horizontal line test. If we were to draw a horizontal line across this, it would pass through an infinite number of points. These are all solutions to y being at a certain height. Say this is 1/2. We have all these different solutions, and that's too many. We really don't want all of that. So what we really need to do is we need to limit the domain of the sine function. So basically what we're going to do is we're going to think about how we limit things so that actually now this graph has been reduced, so we only get one solution when we have a horizontal line cross through it. So here are the three parent graphs for sine, for cosine, and tangent. And you see that they, again, all fail the horizontal line test. So we need to resolve this. Let's look at first the tangent graph. You see how it fails here. But what we're going to do is we're going to just kind of get rid of one of these, or actually all of these, and leave just this middle one here that starts, it has its center at 0 and goes up and down here. You know, the piece that's between negative pi over 2 and pi over 2. So we're going to restrict that, and now it passes the horizontal line test. Let's do the same thing for sine and cosine. For sine, we could use the same exact range. If we kind of were to get rid of all this and all of this, then we have a nice little function right in here. With cosine, we can't do the same thing, because if we use that same range, well, that fails the horizontal line test here. So we're going to actually choose a different range, a different domain region, and so this is what we're going to choose. We're going to just pick this piece right in here. And now all three of these pass the horizontal line test. That's for the sine, cosine, and tangent, but we're interested actually in this discussion for the inverse of each one of these. So we're going to take each one of these and basically, well, we're going to reflect it across the x is equal to y line, and you could think of it as just, if you can imagine this as your x and you imagine this as your y, we're going to start drawing a sine wave here and like this right there. So, you know, if you can imagine, if we were to have continued it, it would have looked like this. And then it would fail the vertical line test. So that's not a function. We want it to be a function. So in this case, we have the range, which is identical to the domain of its inverse here, and that the domain of this function is values from -1 all the way to 1, which was the range of your sine function up here, -1 to 1. Everything gets swapped, if you remember. We have our cosine, and then finally we have our tangent. So instead of going up and down, the inverse goes left and right. Now let's see how we use this graph just for a second. So the inverse sine of 1/2, we kind of know what this should be, but let's just look at it. We're going to look at the x value right in here, 1/2, and find the intersection point here. Find what the y value is, or estimate it. And we can't tell exactly in the graph here, but we know the answer is pi over 6. And so that makes a lot of sense now. We only get one answer. We don't get any of the repeated answers, like 5 pi over 6 would be up here. We get our one answer, and this is the answer the calculator spits out. The calculators basically spit out the one answer associated with each of these graphs. Okay, so let's look at some examples. Arc sine of 1/2. We have one solution that's here. Now, you know, you can, let's just think about, normally we would think, well, there are two solutions. There's a solution in quadrant 1, a solution in quadrant 2. This is 5 pi over 6. But we ignore that one because we've defined arc sine to only exist between negative pi over 2 and pi over 2, so this is our only answer. Next one, we have the arc sine of negative root 3 over 2. And again, if we were just thinking what angles give us a cosine of this negative number, we have two solutions here, but we only consider angles between 0 and pi. So our answer is 5 pi over 6. Here's a bunch of problems here. You can give these a try. I'll show you the answers in 3, 2, 1. Note, no solution because this is bigger than 1. Note for a tangent, you could have a value bigger than 1, less than 1. A tangent, the domain is all real numbers for inverse tangent. Okay, let's look at some of these examples. The tangent of the arc tangent, these are inverse functions, so this value will just be -5. Now you might think the same thing here. Arc sine, sine, inverse functions. Ah, easy. The answer is 5 pi over 3. But no, it's not. Yes, they are inverses, but 5 pi over 3 is not within the legal range of our output. Our output has to be between negative pi over 2. It has to be between negative pi over 2 and pi over 2. So this is the angle. Actually, let me just... The angle is right here. This is 5 pi over 3, but that can't be the answer. Arc sine will never give you the answer that is outside of its range. So it has to return this value. The other expression is, if we were to subtract 2 pi from this, negative pi over 3. Okay, the cosine of the inverse cosine of pi. Again, inverse functions, but this is a little trick problem. There is no inverse cosine of pi because pi is bigger than 1. There is nothing that gives, no angle that when we take the cosine of it gives us a value greater than 1. Okay, final few examples. Tangent of the arc cosine. So to do this, let's draw a picture. We know arc cosine just lives within the top 2 quadrants. So this angle here gives us the proper angle. That gives us a negative 2/3 cosine. The tangent here, we're going to use the Pythagorean theorem. And then we could just see that the tangent in this case will be made up of sine divided by cosine, sorry, opposite divided by adjacent. Okay. Next case here, this is something new. We haven't done this before, where we're given a variable as our value of the cosine. And so we're going to create a triangle. And I could create it in either of these quadrants, but I'll just use quadrant 1, where cosine is adjacent over hypotenuse. So I'm just going to make up any value that gives me a ratio of 3x. And the easiest way is by setting the hypotenuse to 1 and just letting this be 3x. I can make this 2, then this is 6x. Or I can make this 5, and this is 15x. But of course, this is the easiest way. Pythagorean's theorem. And then I have my sine, which is just going to be the ratio of these two pieces. I get my answer. Okay, last one, same exact problem. I'm going to set my hypotenuse value to 1. Here's my sine value right here. Use Pythagorean's theorem to figure out the length of the other leg. And then my cotangent will be then the adjacent over the opposite here. So there you go. Okay, so I have a few problems for you to try out. I'll show you the answers in 3, 2, 1. Okay, that's it. Have a good day, everybody.